Right. So when we think about the electromagnetic spectrum, we usually only think about a tiny part of it, and that tiny part that we think about is visible light. Right. So that's the colors we can see. Right. That's how you can see what I'm writing, the whiteboard, the black pen mark, that kind of thing. But the visible light is only a small part of the electromagnetic EM spectrum. And the reason that we can see visible light is because we have little sensors in our eyeballs that take in this light and then process that to an electrical signal to our brain that then tells us, hey, this is this color. So there's all kinds of other electromagnetic radiation going on around us. However, it's invisible to us because we don't have the correct sensors to see them, right? So rest is invisible to the human eye. So here's just a little infogram about the electromagnetic spectrum. And so we can see we have all kinds of different types of light. We can see that they're all waves. You can see some are kind of bigger waves, some are more squished in waves. But we have all kinds of different types, right? On the left over here, this is very low energy, and then on the right is very high energy light, or not light, electromagnetic radiation. So on the left, we've got radio waves, right? So that's how the radio works, is through these radio waves. Your microwave, also a type of wave. The infrared radiation, we use that for like our night vision and our TV remotes. Then we have this tiny little section of electromagnetic spectrum, which is the visible range. So that's where we can see these different colors. After that, you've got the UV light, and that's a little bit higher energy than visible light, and that's what burns you when you go to the beach and get a sunburn. After that, we've got X-rays, right? Much higher energy radiation. So if you get an X-ray, it allows us to see your bones, but that's obviously something you don't want to do every day because it's not very good for you. And then finally, after after X-rays is gamma rays, which are very, very high energy. So let's take a look at how we describe waves, right? How do we know what the energy or what the color of a wave is? So we'll say, how do we know what color slash type of wave light is? Right? So how do you know if something's a high energy or a low energy type of light? And what we do there is we take a look at the wavelength. So for example, if we have this wave right here, and then this wave right here, right, they're two different waves. Over here, we have the wavelength, which is the distance from the peak to the other peak. So it gets the symbol lambda, and then this is the wavelength. And then the wavelength over here for this wave would be right there. So we can tell that the one on the left has a bigger wavelength and the one on the right has a smaller wavelength. So when it comes to energy, a big wavelength will be a low energy type of light. A small wavelength will be a high energy type of light. And so we can see right here, right? You can see that in the same diagram. Over here on the gamma rays, you can see the wave is very compressed, very small wavelength. And then on the other side, with the radio waves, you can see it's a very big, very long, very large wavelength. So if we think about the visible spectrum, we have our colors, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, right? When you're talking about the red, that's low energy light. And then when you're talking about the violet, that's high energy light. Over to the right here, we've got UV light, right? Ultraviolet light, that's what gives you the sunburn. I like to memorize that the violet is the high energy light because right after it comes the ultraviolet, which we know gives us sunburn. So one way to talk about wavelength is to talk about the actual wavelength, but there's another measurement we can use that's pretty much the same thing as wavelength, and that's frequency. It gets this fancy V symbol. And frequency is the number of crests that pass through a point in 1 second. So this is often given the symbol hertz, and it's equal to cycles per second. So for example, if you had a frequency of 5 hertz, that means that 5 crests would pass through a point in 1 second. And if we think about frequency, right, the more compressed our wave is, so if we take a look at this kind of right here, the more of those are going to pass through a point in 1 second than some kind of big wavelength. And so frequency is inversely proportional. So it's the opposite of wavelength. So if you have a high wavelength or a large wavelength, you have a low frequency, and vice versa. If you have a high frequency, you have a small wavelength. We can also think about it mathematically. Frequency is simply equal to the speed of light, which is that 2.998 times 10 to the 8 meters per second divided by the wavelength. So it's just another way to say the same thing. All right, so let's draw 2 more waves. So we'll draw a wave that looks like this, and then a wave that looks like this. If we think about these 2 waves, at least if my drawing's good enough, we can see that they have the same wavelength. And if they have the same wavelength, they also have the same frequency. Their difference is the amplitude, right? The height of the wave. So that's in purple. And so what's the visual difference between these? A lot of people are going to think, oh, one's a higher, one's a lower energy light, so they're different colors. But remember, it's the wavelength that determines the color of the light. So these would be the same color or same type of light. Their difference would be its brightness. So when we have a bigger amplitude, like that lower wavelength, right, we have this taller amplitude, it's a brighter light. All right, and so this is how light was thought of. Light was thought of as waves for a long time, and it was thought that basically waves and matter were 2 completely separate ideas, and that some things were described as waves and some things were described by matter. But then it got a little bit complicated when Einstein came around, and Einstein proved that light also sometimes acts as a particle. And this is called wave-particle duality. And it was in this time that quantum mechanics came around, and our universe kind of got a lot more complicated, but we also understood it a lot better. So what we're going to be going through next is just a little bit of background behind quantum mechanics. Some of it can be very complicated, and we're not going to go very in depth. If you're wondering, all right, what do I need to take away from this? Go ahead, take a look at the work along and the homework checks to kind of know what you actually need to know versus what's kind of more historical or just background information.